Okay, in this video we are going to be starting our 8th module, and this module is going to be on statics and torque. Everything we're going to be talking about here is somewhat based on chapter 9 in the textbook. The textbook goes into a little bit of extra stuff that we're not going to be interested in, so looking at the textbook right now, we are interested in equilibrium, so we're going to be interested in sections 9.1 and 9.2 where we talk about the first two, well, the two conditions of equilibrium. We're also going to talk about that in this video, and we're going to introduce torque. Torque is really the sort of key topic that I'm trying to get at in this module. We're going to do a number of examples using torque. And we're going to talk about stability as well, which is covered in section 9.3, but that's pretty much all that we're going to be using from this chapter. So we'll do a number of examples. We'll look at, well, as I mentioned, 9.1, 9.2, 9.3. Some of the ideas from 9.4 might be useful, some of the problem-solving strategies, but basically it's all going to be examples involving torque. So torque is really the sort of idea that underlies everything that we're going to be working on in this module. Okay, so we can probably get started here. I guess I'll start by talking about statics. So statics are is the study of forces in equilibrium. There are two conditions that have to be met for a body to be considered in a state of equilibrium. The first condition is that we require that there are no net external forces on the system. So we can see that here. So we have no net external force. Oh, and I have this turned on. So we have no net external force, and so what does that mean? Well, we have no force in any direction, which means that we have no acceleration in any direction, and so our velocity is constant. Okay. But this requirement of no net external force on its own isn't enough for us to get equilibrium, and so we consider the following situation. We can see here that we have a sort of macroscopic object, so it's not a point-like object. It's an object that has some size in some dimension, right? It has some width, some height, some thickness, whatever. We can see here in the first case, in this case A, I'll label it, that we're applying forces in such a way that they would perfectly sort of counterbalance, right? So this object would be in equilibrium. But we can see here in case B that even though our net external force is equal to 0, let's say these two forces were equal and opposite, right? But the way in which we're applying it to this macroscopic object is going to cause this object to start to spin more and more quickly, right? It'll start spinning around a pivot, say somewhere here, and it'll start to rotate more and more quickly. This is a problem. And this is something that we sort of need to get rid of to really achieve an equilibrium for this object. And this is where the second equilibrium condition comes in. We require that the angular velocity of the system be constant, right? So we need a constant omega. So this thing is if it's rotating at a constant angular velocity. It's not an accelerating angular velocity, right? And we've seen angular velocity before, but now we want to talk about what could change angular velocity. Okay, so well, we just saw the answer to that question. We just saw that applying forces in such a way that a torque is created will lead to changes in our angular velocity omega here. And I just used the word torque, and that's sort of what we're going to be getting at here, right? So we need to apply this torque to create changes in omega. Okay, so we define torque mathematically as we see here. So torque, and this symbol that you see here is a tau, so we give torque the symbol tau. And so we write torque as tau is equal to Rf sine theta, where the R is the distance from the pivot that the force F is applied. F is the magnitude of our force, and theta is the angle between them. So you can see it here in this drawing that I've pre-drawn over here. We see that we have some sort of a stick or something here. And if we consider the pivot that I've drawn on here, this dot, and we're applying some force to this stick up over here, this r is meant to give us the distance from the pivot to the point where we're applying this force, and theta is the angle between that force vector and our r here. So what do we sort of have here? How do we increase torque? Well, we can see that for any angle, so we can imagine that this angle f, well, this angle between r and f can change. It can go anywhere between 0 and 180 degrees, right? So we can imagine the f pointing directly down the stick toward the pivot, or directly away. But since we're taking the sine of this, and since this angle is always going to be between 0 and 180 degrees, as theta gets closer to 90, sine gets closer to 1 from either side, right? And our maximum value for sine theta is going to be 1, right? So the closer that our angle is to giving us a sort of perpendicular application of this force to the object, the higher our torque is going to be. Also, if we raise r, like if we apply this force further out along the stick, then we're going to have a higher torque. And the same is true for cranking up f. If we crank up the amount of force that we're applying, we're going to have a higher torque. Quick note about the SI units of torque. The SI units of torque are just going to be Newton meters. So we'll try to use that wherever we can. Now, one question might be, does it matter which angle we take to be theta? And I've left some space here to have a quick little discussion. We can imagine, I'm just going to draw this kind of quickly, we can imagine that we have our stick here, and so whatever, we have our pivot here, and we have our R here, but we have a force being applied like this, let's say. And now, does it matter if we choose this to be theta, the smaller angle, or the larger angle to be theta, right? As long as this full sort of arc is 180 degrees. Well, it turns out that it doesn't matter, right? It doesn't matter which one we choose because of the way that sine works, right? So we can think of a unit circle. So imagine a unit circle. I'll draw some coordinates on the unit circle here. And so we have some angle in here. Let's call this this angle theta. Okay. So what is sine calculating? Well, sine is always calculating the height. And I'll draw this a little longer so that I can get some more drawing in here. But sine is always giving us this height, right? Sine gives us this height. Well, the sine of that angle theta gives us that height, and the cosine of that angle would give us this length, this width here, right? But so it doesn't really matter if we look at this one or we look at the exact opposite, which would just be 180 minus theta, right? So if we had this angle in here, this would also be theta, except we could also think of this as the full, let me use a different color here, as the full 180 degrees minus theta, right? So if we go right out to there, it's 180 degrees minus theta. But in whichever case, we still end up having the same vertical value here, right? So our sine, basically, no matter whether we choose this value for theta or this value for theta, whichever angle that this thing makes with our r, we're going to end up with the same value for sine theta, right? So in the end, it doesn't matter. Basically, all this to say that this choice between two different thetas doesn't really matter. Okay. And so the textbook also goes into this discussion somewhat, and I kind of want to flag this discussion a little bit because they talk a little bit about this value r perpendicular, right? And they set up r perpendicular to be r sine theta, and then they talk about sort of applying. Well, here I'll draw a picture. This is going to be my attempt at duplicating figure 9.6. D in the textbook. Okay, so they talk about some sort of a door or something here, where they're applying a force like this at some r. This is our f. That's a terrible looking r. And so they talk about sort of tracing out this f back, and then building. Well, they have some angle in here, right? They have some angle theta here. And this is our r, and then they build out what they call R perpendicular here. So if this sort of idea helps you guys calculate, by all means use it, but I find that it's an extra step. This whole building of R perpendicular is just a way of separating out the idea of calculating r sine theta, because in the end all you're really doing to find r perpendicular is you're calculating r sine theta. So they kind of break it up into two steps. They calculate r sine theta, they call it r perpendicular, and then they put it back into this tau formula up here, and they call this r perpendicular. Then they go on to calculate tau. I prefer to just memorize the one formula, so I only keep this in my head, and I just calculate sort of from the beginning and think about the angle rather than calculating this r perpendicular. So again, if you guys find it easier to calculate r perpendicular first and then go to tau, by all means feel free to do that. Or if not, just do it sort of the way that I do it. I find that easier. Maybe a quick note here: if you're given this angle that I have in this drawing here, how do you know what the angle between R and F is? Well, you can always think of it, and maybe here I'll do it in red. You can always think of this as being a line and this as being a line, right? And we know that if we know this angle in here is theta, it's also true that if these are straight lines, this has to also be theta, okay? And this angle here, I'll do it in green, this angle here would have to be 180 degrees minus theta, and that's also true for this this angle here. Okay. So that's just a sort of quick discussion on these different angles and the sort of difference in the way the textbook chooses to sort of address some of these problems and the way that we'll be addressing them. I mean, in the end, they talk about sort of both ways, so we'll be choosing to sort of ignore this r perpendicular and just think of tau as rf sine theta all the time. Okay. So let me move on from here. And so now that we have this idea of tau, of our torque in mind, we can sort of rephrase this second equilibrium condition in terms of this torque. And so the second equilibrium condition becomes that we require that there are no net external torques on the system. We require a net external torque of 0 on the system. Okay, and so this will ensure that we don't have any changing angular velocity, right? So our omega will stay constant if we have no net external torque on the system. Okay, so I think that we'll be finishing this video off with an example. So here's an example where we're going to make use of this idea of torque and this idea of systems being in equilibrium. Okay, and so the example here is from the text. We're looking at two children that are on a seesaw. The seesaw itself has negligible mass, and the seesaw is in balance, right? So it's in equilibrium. This thing is not moving; it's just perfectly stationary. And so the seesaw has the configuration that we see below here. So I've drawn it out here. We have a child of mass 1 on the left, child of mass 2 on the right. We see the forces. The force of gravity sort of supplied by their mass on the seesaw. We see that we have this sort of central pivot here that the seesaw sits on. And what are we trying to find? Well, we're given these values over here. We know that M1 is equal to 26 kilograms, M2 is 32 kilograms. R1, this distance in here, is 1.6 meters. We don't know what R2 is, and we know what theta 1 and theta 2 are. They're both 90 degrees. So we're trying to find what R2 is, and then we want to find what FP is, and FP is just the force that the central pivot is exerting upward on the seesaw. Okay, and so let's get right to the problem here. So I think I have some numbers that I've calculated here. I do. Okay, so we're told originally that the system is in equilibrium, right? That this thing is not moving, that the whole thing is balanced, right? And so what does that tell us? Well, let's take a look at the second equilibrium condition. That tells us that our net torque needs to be equal to 0, right? And so this maybe since this is our first time working with it, I'll label it. This is equilibrium condition 2. Okay, and so we know that the net torque needs to be 0 on the system. I've also labeled up here on the diagram a positive direction for the torque here. So I'm going to be thinking of, I'll generally think of counterclockwise as our positive direction for torque. And so we're going to have some torque supplied by M1, right? So we have the force of gravity pushing us in this direction. So it's going to be tending to rotate the system in a counterclockwise direction. So when we add up the net torques, we're going to have torque 1 in a positive direction, but Fg2 here, our torque supplied by M2, is going to be in a negative direction, right? It's going to be operating in a clockwise direction, not counterclockwise, and so our torque 2 will be in a negative direction, okay? And we can rewrite these two torques in terms of the definition that we laid out up here. So Rf sine theta. Let's do that. So we're going to have R1 F1 sine theta 1, excuse me, minus R2 F2 sine theta 2. And we're told that both theta 1 and theta 2 are 90 degrees, right? And so we can simplify that. Sine of 90 degrees is always 1. And so we have R1 F1 minus R2 F2. And remember that this is equal to 0. So we can rearrange this to give us R1 F1 equals R2 F2, right? But we can replace F1 and F2, right? Because we know that F1 is really Fg1, right? It's the force of gravity that's supplying that torque in that direction. And Fg2 will be F2. So we have R1 Fg1 equals R2 Fg2. And what are we looking for here? We know what Fg1 and Fg2 will be. We know the mass, and we know that that's just going to be mg, right? And we know what R1 is, so we need to find R2. So maybe I will not waste the rest of this page, and I'll shift over to here. We can then isolate R2. So let's do that. R2 is going to be equal to R1 Fg1 over Fg2, and one more simplification. We're just going to put in our masses and gravitational acceleration for the two forces of gravity there. So we're going to have Gm1 over Gm2. These g's will cancel, and we're left with R1 M1 over M2. Okay, and so at this point we're just at the point where we want to substitute in numbers. I'll do that here. R2 is going to be equal to, what's R1? 1.6. Then we have M1 is 26 over 32 for M2. If we run the calculation, we're going to find that this is equal to 1.3 meters. So when this heavier child is at a distance of 1.3 meters from the pivot, and the lighter child is at 1.6 meters, this system will no longer, or won't have any net torque applied to it, so it'll have a constant angular velocity of 0. It won't be rotating, right? Does this match our intuition? Well, it kind of does, right? If you think about sitting on a seesaw and you're heavier than the person that you're sitting with, then you need to sit closer to that point where the seesaw rotates around so that the whole system stays in equilibrium, right? So that's good. Whenever we can do a sort of sanity check versus our intuition, it's always a good idea. And in this case, it checks out. And so now, so this was the answer to part A. In part B, we want to solve for FP. Right, and FP, so this is kind of simple, right? We've done this a number of times. This is just going to be an application of Newton's second law, right? And so we know that we're in equilibrium. So our first equilibrium condition tells us that F net needs to be equal to 0. Maybe I won't make it a vector here. So f net needs to be equal to 0. This tells us that our f net in any direction has to be equal to 0, but we'll say this time we're interested in the y direction because both of our gravitational forces are operating in the negative y direction, and fp is operating in the positive y direction by the sort of coordinates that we've set up here. And so we know that f net in the y direction needs to be equal to 0, but it's also equal to, it's also equal to fp in the positive direction and minus fg1 minus fg2 in that negative direction, right? And so now we can solve for fp as we've often done before. And just cleaning things up, we won't have to discuss this too much again because we've done this many times before. We're going to find that fp is equal to m1g plus m2g. We can clean that up a little bit to just say g m1 plus m2. And at this point we can substitute in numbers. This gives us an fp equal to 9.8 times 26 plus 32, which gives us a total of 568 newtons for fp. Okay, and so that's sort of our first example of working with torque, and really this kind of gets to everything that we need in the chapter. So I'm going to do at least one more video, perhaps two on this one. It's a fairly short module, but those videos or that video will focus only on examples at this point. We've already covered all the new physics that we're going to be doing in this module. Now it's just a matter of applying it and problem solving with it. Okay, and so I'll see you guys in the next one.